Okay, so let's get started here. So last week, Chopin just introduced the basic bosonic systems, like the canonical operators and the basic bosonic code, including the binomial simple binomial code. So this week, today, he's going to talk about some other bosonic code like cat codes or the GKP codes. So let me hand over to Chopin.
Thanks.
Thank
Yeah,
you.
so this is the second and actually the last tutorial on bosonic codes. We decided to cut down on one. So I'm going to talk about some more codes, as soon mentioned, the CAT codes and GKP codes mostly, and also some more background that will be required to understand those codes. So let's get started. Maybe I can recap a little bit first. So we saw that bosonic encodings or bosonic system simply means that you have a simple harmonic oscillator, and we work with the Hilbert space of such a system and try to encode quantum information in that. So there's some differences between the normal qubit encodings and bosonic encodings. For example, is that in two qubits, in a qubit, you just have two basis states, but for a bosonic system, you have an infinite number of basis states. So there's more freedom to encode information. And for a qubit system, we typically require multiple qubits because you only have access to two states if you have a single qubit. But since we have an infinite number of states in the bosonic system, we can encode large amounts of information. We can encode large distance codes, all within a single mode. So that's one advantage of the bosonic codes. We also introduced some different bases for these simple harmonic oscillators. The most canonical ones are these position and momentum bases, which just which are which just tells you where your particle is in a classical sense, but in a more abstract sense, these are just some states which are delta orthogonal, and they're labeled by elements of the real field. Same for the this is quite analogous for the position basis and also the momentum basis. Just two different ways of representing the same wave function or the same state. Then we looked at this other basis, which was the most useful for us for the binomial codes, which was this Fock basis. And instead of being labeled by a continuous set of elements like the field R, we now label this by positive integers. So every positive integer denotes one orthogonal state. Again, these are also orthogonal and complete. We also call these number states sometimes. And some of these operators that were useful to us were these number operators, which tells you how many photons you have or how much is the energy in your system. And then we had these annihilation and creation operators, which either destroys or creates a quanta of energy. So an annihilation operator in the Hilbert space would bring you down one level, and a creation operator brings you up one level in this Hilbert phase, which is labeled by the energy labels here. So that is about the bases. And then we also looked at one basic error model, or two basic error models, which were these photon loss and the dephasing errors. So just to remind ourselves, photon loss works. Uh, they're just implemented by these annihilation operators. So they work like this. If you have a state somewhere in your Hilbert space, n equals n naught, then an annihilation operator, which is a cross operator of this error channel, would bring you down one level to n equals n naught minus 1. And dephasing operator works in a simple way as well. It's generated by the number operator. So for any Fock state, it just adds this sort of phase to your state. And against this simple, photon loss is actually the most dominant error model in a lot of systems, and this is the most interesting model for studying error correction in bosonic codes. Um, and we looked at this one code called the binomial code, which can actually protect against dephasing and photon loss. And in general, this code looks like this. So in your single mode Hilbert space, this ladder, you would choose some states which have some spacing. For example, I'm doing this for a single loss code. And so all the red, this has to be one above, this two, no. Oh no, actually this is fine. two, one, two. Yeah. Yeah. So you would choose these states which have some spacing between them, such that whenever any loss error happens, the states don't overlap with each other. Like these blue balls never go to these red balls. So you can distinguish which error happened and then you can correct against them. So if you want to correct more losses, you would choose the separation to be higher. This is what I denoted as S plus 1 here. And this S determines how many losses you can correct. But in general, there's a simple expression for these binomial codes which you can tailor to protect against any number of losses or any number of dephasing errors. So which is this error set here, up to D dephasings, up to L losses, and actually you can also correct against up to G photon gain errors, which would just be the same action but the other way. So these would be implemented by the creation operators. Okay, so this is all about last time. Now we can start talking about something new. So the agenda for today is to talk about these CAD codes and GKP codes. CAD codes are coherent state-based codes, and I've not introduced coherent states yet, but I'll do that in the next slide. And these are predominantly constructed to protect against the loss channel. And because just by virtue of construction, the dephasing noise is actually exponentially suppressed in these codes. So we mostly only care about the loss channel, and we will see how these kinds of codes can protect against the loss channel. This figure might not mean anything at this moment, but it'll make more sense in a few slides. Then there are GKP codes, which are phase-space states-based codes. So phase space just means like X and P eigenstates. So these are based on this position and momentum eigenstates, and these are designed to protect against the displacement channel. And I will talk about what the displacement channel is. Yeah, so let's get started on this. First thing is these coherent states. So this is the fourth and the final basis that I'm going to introduce in these tutorials. This is again just another basis, so you can implement this via unitary by a basis just by a basis change. These are labeled by complex numbers now, not real numbers or integers, and every complex number denotes one coherent state. One good thing about them is that they are the eigenstates of the annihilation operator. So if you act on any of these coherent states with the a hat operator, you just get a constant out front. So these are very simple to work with when you're dealing with annihilation operators, and in particular the loss channel. These are not orthogonal. This is the first example of a basis which is not orthogonal or delta orthogonal. So the overlap between any two different coherent states, it is exponentially suppressed, but it is non-zero. But actually, for most practical purposes, if alpha and beta are big enough, like even if the value of alpha beta, the mod of alpha beta is 2 or higher, this exponential is sort of insignificant. So we can always approximate this inner product to actually be just 0. So we can assume that all of these coherent states are actually orthogonal, whereas in reality they are not. Um, and they are also complete. So you can represent any state by just expanding it in terms of these coherent states. So these states are almost orthogonal and but complete. Just to get a picture, I mean, we all are familiar with complex numbers, but every point in the complex plane like this would represent one coherent state. So this is a different coherent state, different coherent state, different coherent state, and so on. Um, Yeah, and as I mentioned, it is useful because the loss operator is simply an eigenoperator of these states. So when we're dealing with the loss channel, it becomes quite easy to understand and analyze when working in this basis. And just for completeness, we can expand it in the Fock basis as this. It's a simple expression. Um, so the one thing to note here is that it is a superposition of each Fock state with a non-zero coefficient. So it gets contribution from every Fock state. So if you measure it in the Fock basis, the state is going to completely collapse. And yeah, let me just say that. So it has contribution from every Fock state. Uh, okay, let's move on. Uh, the noise. Yeah, let's look at some basic examples of the CAD code. So again, we have our dephasing noise and the loss noise. Dephasing noise in this, for the purpose of CAD codes, I'm not gonna just denote it by the n hat, but I'm going to say that it is generated by the n hat operator, so just exponentials of n hat. And I mean, if you expand it, then this will just give you n hat till the till the first order approximation. So this is really the dephasing noise. We just represent it in a different way. It's nice to represent it in this way because the action of this operator is quite simple to understand in the coherent state language. So if we have a circle, let's say we only consider coherent states such that the mod of alpha equals 1. So all of these states now lie on a circle. And let's say we started out with this Fock state, which is alpha equals 1. Then the action of this dephasing operator, e to the I n hat theta, is very simple. It just rotates you into this state. So let me just write it down, is the action of this operator, which is generated by dephasing, is just to give you a state which is this. Notice that this is not a phase factor anymore because this is not outside the cat. This is actually changing the state internally. Like this is not just giving you a phase on the state, but it is actually changing the basis state. Yeah. And the loss noise is the same thing. It is just implemented by these annihilation operators. So let's see this first example of a cat code. Um, yeah, let's draw it out. So we are again working on a circle. So we'll assume that alpha mod alpha equals 1. So everything is on a circle. And this first zero state, this is just going to be alpha plus superposition of alpha and minus alpha. So these 2 points. And the second state is a superposition of I alpha and minus I alpha with equal contributions. So these are the code states. And I draw these because, yeah, this is just, you can imagine them as line segments which are embedded in a circle. So this is going to be the code state that we have to deal with. And we'll see how this corrects against all of our noise models. So my first claim would be that this CAD code protects against dephasing up to dephasing error of this sort for phi up to pi over 4. And this is not too hard to see because I said that this was our CAD code. The red state is the zero state and the green is the one state. So when this noise is applied, u phi, which I call this e to the I n hat phi, then the zero state is yeah, zero state is rotated by an angle phi. This one state is also rotated by an angle phi. So all of these points are rotated by an angle phi. And if the angle phi is not big enough, and by big enough I mean like if it doesn't cross this threshold, then we can indistinctly determine which point this resultant state started out with. So like if we just consider one state and we started out here, and there's another state here. So if the angle phi is less than pi over 4, then we never get into this territory. And if we just measure the angle of this resultant state, let's say it landed up here, we measure the angle theta mod pi over 4, then we would know where in this region we ended up upon, and we can correct it back to the original state. Whereas if it had landed up here and we did this measurement mod pi over 4, then we would have mistakenly said that, okay, maybe this state started from here, and we would have corrected back to here. So that would have been a logical error. That's why we have these green regions and the red regions. These red regions are everywhere this zero state could land up on for us to correct it, and this green region is everywhere this one state could land up for us to correct it. And this angle is just pi over 4. So in this, because of this reason, we can this particular CAD code can correct against any dephasing noise for a rotation angle less than pi over 4. And the correction is very simple. You just implement minus I n hat phi, where this phi is what we determined by our measurement. So yeah, the more highly separated your points are, the better protection we have against dephasing. And this is just an intuitive picture of how this code protects against these dephasing errors. We will make it more concrete with the KL conditions in a few more slides, but this is essentially how it works. Um, okay, next we can talk about the loss errors. And this works in a similar way to the binomial codes, where if you take your CAD codes, which was this, which were the 0 and 1 states, and you just change the basis as in, like this. If you imagine this as the computational basis states, then you just take a superposition and you choose another basis for the logical states, this plus and minus basis. Then they turn out to be the superpositions in the Fock states of even or of even Fock states. So what I mean is this plus state is just a superposition of everything mod 4. So 0 state, 4 state, 8 state, and so on. And this minus state is, and this is written here actually. So this minus state is a superposition of every Fock number, which is 2 mod 4. So the 2 state plus 4, 6 plus 4, 10, and so on. The difference from the binomial codes is that for this particular code, the superposition is infinite. So you don't truncate anywhere here. Um, this superposition goes on till infinity. So you have all the Fock numbers included in this, which satisfy this condition of being 0 mod 4 or 2 mod 4. And the correction works in exactly the same way as the binomial code. So if you have a single photon loss error, then everything would go down one level and you go from a even parity state to an odd parity state. So to detect this error, you can just measure the parity of the system mod 2 or the parity of the system. And if you end up with an odd parity, you know that one loss happened and you can correct it. If you detect that it's still an even parity state, then no loss error happened. And essentially there was no error on the system to begin with. So this is intuitively how it corrects against loss errors. And now we can look at more rigorously using these nil-of-Lam conditions, how these codes work. Right. So first dephasing, we have these operators u theta and u phi, which brings about these errors. Um, u theta dagger u phi is just going to be equal to u of phi minus theta, because the operators would be something like this. And since n hat and n hat obviously commute, this is just equal to e to the I n hat phi minus theta, which is u of phi minus theta. So we only need to check this condition, and we can, yeah, we can just see it from this picture is that if we had a zero state and an angle phi minus theta rotation happens, it lands up somewhere here. So we land up in this state, like every alpha just goes to alpha times e to the I phi minus theta. And as long as it doesn't have an overlap with the one state, then we're good. So like if the one state which is part of this zero code, it lands up here, and if this state doesn't have an overlap with the closest point would be this guy, which is the state I hat. So we can check the overlap of I with not like so we can check the overlap of this guy, and this becomes, I'm going to write I as pi over 2. So as long as this is not true, then we are good. And the maximum value of phi minus theta can be pi over 4 because of this condition. So as long as theta and phi are both less than pi over 4, then there is no overlap ever between the 0 and the 1 state, and essentially all of these KL conditions are satisfied. Um, yeah, maybe that was a bit too quick, but I hope that made sense. We can take questions later on this. For the loss error, it's again very simple to see. Like in the binomial case, you just check these operators a dagger, a, and a dagger. And because of the separation between the states, um, there's never any overlap between the red and the green states. And so the KL conditions are satisfied, just like in the binomial case. And it's also quite easy to see that this doesn't work for two photon loss errors because you go from even parity to even parity again. And so then there's an overlap between the 0 and the 1 states when you have two loss errors, and it can actually create a logical error. So like this red state, which had 0, 4, 8 states, upon the action of this a squared error, we go to, mm, I don't know what this is. Yeah, no, we just go to these other states. And this was actually like this blue one was actually the one minus state. So the plus state has actually gone to the minus state because of the action of these two photon loss errors. And so we cannot correct against two photon losses, only one. Um, right. Then, like the binomial codes also, these have a more general analog where you can protect against more errors. So in general, you can make a CAD code in this sense where you have, mm, yeah, this should be phases actually. I forgot to mention this. So this should actually be exponential of these things. 2 pi over qs plus 1 k plus j. Um, so what this is saying is that for correcting against S errors, you choose points on your sphere which are equal superpositions of points which are uniformly separated. That was a lot of words. So for example, if you want to have correction against two loss errors and you want to have three code words, so this will be the logical dimensions. We're going outside of the qubit world. Now we have a qubit here. So what we will do is we will divide this whole sphere into three times 2 plus 1 is equal to 9 points. So there will be this, um, 1, 2, 3, 4, 5, 6, 7, 8, 4, 5, 6, 7, 8, 9 points. And you would choose every third point as being one state. So this guy, and this guy. So this would be one code state. These are not really uniformly separated as I've drawn them, but we would want them to be uniformly separated. Then this guy would be another code state. And let me use maybe blue or black. This guy, this guy, this guy. This would be the third code state. So 0, 1, and 2. And we can see that dephasing error is still valid. Like we can protect against dephasing because of this separation between the points. So like if the dephasing takes you anywhere in this region, then we can measure this thing modulo 2 pi over qs plus 1, and we can rotate it back. So dephasing up to this angle is still valid. And protection against loss happens because, again, when we change the basis of this to this other z error, let's say the equivalent of the plus minus basis for three states, then we would see that these are again separated, and these are more separated now. Uh, so these would be separated not by one, but a gap of two between each support of the Fox face. So this would be 1, 2, 3, 1, 2, 3. Yeah, we'll see that. Uh, yeah, so there is now a separation of three, so that even if two loss errors happen, this blue state doesn't go to the green state, and the same for everything else. So this can actually correct against two loss errors. Um, yeah, so the CAD codes are quite analogous to binomial codes in that sense. It's just easier to see that it protects against dephasing because of this picture of the coherent space and the circle. And when you convert it to this Fock state picture, then it's exactly analogous to how the binomial codes work for the protection losses. So yeah, I hope that was clear. And this was all about the coherent states and the CAD codes, which is the second kind of encoding we have seen. You can generalize it to multi-modes, and I will mention that a little bit in the end. So you can generalize it to multi-modes, so you can have as many points on the circle as you want to increase the level of your protection. But of course, there's also this trade-off that when you increase your loss protection errors, you would need to have more states which are embedded in the same circle, and that would mean that you are decreasing your dephasing distance. So the trade-off is between loss and dephasing. The more you can protect against loss, the less you can protect against dephasing. And this always happens in error correcting codes, that you can protect, maybe get a better X distance while trading off the Z distance, or the other way around in qubit codes as well. Um, yeah, okay. So maybe we can move on to the second part of this tutorial now, which are these GKP codes and displacement error channels. So before going to the displacement error channel, maybe I can mention what displacements are. So this is going to be a little bit abstract for a few minutes, but bear with it. So displacements are Gaussian operations, which means that any Gaussian state, when you apply a Gaussian operation to it, it goes again to another Gaussian state. And I haven't even told everybody what Gaussian states are, so this is still quite nonsensical. But yeah, so what are Gaussian states? These are states whose Wigner functions are Gaussian, whose Wigner functions have a Gaussian nature. So Wigner functions, I'm not going to give the definition because it will take too much time, but Wigner functions can just be imagined as some quasi probability functions. So looking at a Wigner function, you can tell something about what is the probability of finding your system or particle in the particular state. For example, if I want to plot a Wigner function of this state, of this position state, which is situated at x0, so it's definitely at x0 with a certainty of 1, then this would look like this. This would be the Wigner function of this state. Um, and this would just be a delta function at the point x0. So looking at this Wigner function, we will be able to tell that this particle is in the state x0 because there's a probability of 1, or there's this peak probability at x0. So this is intuitively what a Wigner function is used for, is it's a quasi-probability distribution in phase space. We typically plot it in the phase space, not any other like Fock basis or the coherent state basis. Um, so let me just give another example of these Wigner functions and how this works. So this is how you would write down a displacement operator, which is this exponential of beta a dagger minus beta star a. And beta would be the uh, what I would call, like, beta is the parameter which characterizes how much you're displacing your system. And these a daggers and a's are of course the creation and annihilation operators. So the action of this displacement operation is quite simple in the coherent state basis as well. So if you act with the displacement of beta on a coherent state alpha, then you just get a state alpha plus beta with some phase. But this is the important part, is that applying a displacement operator on a coherent state just displaces it by this parameter, which characterizes their operator. And this is again a Wigner function of a coherent state, alpha. So this is the complex plane. This is plotted on the complex plane, and this Wigner function is actually just a Gaussian curve, or a Gaussian function, which is centered at alpha. So this is a Wigner function of any coherent state. And when you apply yeah, maybe I should call this something else because, yeah, maybe let's call this, or I'll just say this. So this is the Wigner function of an alpha coherent state. When you apply a displacement by beta, then this thing just goes from alpha to alpha plus beta. This whole Wigner function, this whole Gaussian function is just displaced. And this comes back to the definition of displacement operator also, is that it's a Gaussian operator in that it took this one Gaussian function and it converted it into another Gaussian function, which is just translated. So that's the definition of a Gaussian operation, and its displacement is an example of a Gaussian operation, which just displaces coherent states by a simple number, which is the parameter characterizing the operator. So the bottom line I think we need to remember is this. Everything else on the slide is just background or jargon. Like this is going to be a bit more busy slide where I'll describe some relations of these displacement operators with the position operators, the momentum operators, the coherent states, and so on. And this will be operationally useful for us to understand the GKP codes. So first of all, if you conjugate the position operator by these displacements, then you just get the displacement, then you just get the position operator plus something else. So it also displaces the states in their position basis. So again, the bottom line here would be this. So if you started out with the state x in the position basis, then applying a displacement operator would just give you a displacement of this form. So these are just some factors, but the important part is this. The position state is displaced by the real part of alpha. And similarly, the momentum states are displaced by the imaginary part of alpha. So this is the action of the displacement operator on the position and momentum states. And what else did I want to say? Hmm. Yeah, never mind that. So then the other thing is this, these operators almost commute in the sense that if you apply d alpha first and then you apply d beta, so as you would imagine, this would just bring about a displacement of alpha plus beta. So starting out with some state, like if you started out in your space with position with some state which was labeled by some gamma. So this is situated at gamma. Then applying d alpha brings you to alpha plus gamma, and then uh, applying beta brings you to alpha plus gamma plus beta. And this is true, except that you also get this phase now with the resultant state. So yeah, you get a composition of alpha plus beta with this phase, and if you look at it in terms of the commutation relations, then we can easily see that d alpha and d beta commute if and only if this phase is 0 mod pi, of course, um, because of this relation. So d beta d alpha is just d alpha d beta times this phase. So if this phase is a multiple of 2 pi, then these operators exactly commute, which is exactly this condition. So we can just check the imaginary part of this complex number product, and if it is 0 mod pi, then these operators commute. And this would be important for us to understand the stabilizers of the GKP codes. Finally, I can mention what the displacement noise channel looks like. So we call it the AWGN, or the additive Gaussian wide noise. It is implemented by this super operator here. So n of rho acts on rho, where rho is some density matrix. So you can imagine this as this operator where psi is some state, and it acts as the following. So it conjugates the density matrix by this displacement operator, and the amount of displacement has some probability distribution p sigma tilde. Now this p sigma tilde again is just a Gaussian, which means that the if this was the probability of x displacement x plotted with x, then this decays exponentially if you increase your x. So which means that the probability of large displacements is very, very low. Yeah. So for our error model, we would typically just look at small displacements, i.e. operators of this form, where alpha is less than some value, let's say d, where d we can call sort of the distance of the course we would be interested in. So a code would protect against code would have a distance d if it can protect against all displacements which satisfies this condition. The displacement, the norm of the displacement is less than d. So that would be a distance d code against this AWGN. Okay, finally we can move on to the next kind of code, which is the GKP code. This is a nice definition that I took from Jonathan Conrad's PhD thesis, who is one of the world's leading experts on GKP codes. So a GKP code is a stabilizer code acting on the Hilbert space of n bosonic modes, where stabilizers are given by displacement operators. So this is going to be actually the first stabilizer code that we see in the bosonic language. It can generally it can generally be defined on a Hilbert space of n bosonic modes. But for this next particular example, I'm just going to work with n equals 1 for simplicity. And it's the first stabilizer code, and the stabilizers are given by displacement operators, which I will also describe. So yeah, very simply, if we just want to view what a GKP code looks like, it is equally spaced points in your x basis or the momentum basis. So this is the line which denotes x, and this is the line which denotes the momentum eigenvalues. So a GKP code can be defined on either of these, and these are interchangeable. This is just again a change of basis. So a simple GKP code is this. You take some amount of region, which is this D. So all of this separation is D, and you take equal superpositions um, of these points which are displaced by Q times D, where Q is the amount of information you're trying to encode. So in this case, I have chosen Q equals 3. So you'll see three different colors, this red, blue, and green. The superposition of all these red points is one state, the superposition of blue points is another, and the superposition of green is another. And all of these states are displaced by a quantity d. So yeah, this is very simply what a GKP code looks like, and this is all there is to it. I mean, this is how you define a GKP code. If you just convert it into the momentum basis, then this alpha, oh sorry, this was not alpha, this was d, this was alpha. So the displacement was d, alpha. Uh, yeah, I don't know. Yeah, this was alpha. And then when you convert it into the momentum basis, this alpha just gets converted into 2 pi over alpha. So you have similarly equally spaced states, which are spaced by this quantity 2 pi over alpha. And if we take over our binomial cat code intuition again, it is easy to see that this can correct against displacements, this can correct against all displacements beta. So all errors of this kind, where the real part of beta is less than equal to alpha over 2, so that we are still in this region. And there's a root 2 because of the action that we saw on the previous slide. And the imaginary part is less than 2 pi over 2 alpha over root 2, so that we are still in this region. And we can again do these measurements modulo 2 pi over 2 alpha, or pi or alpha over 2. And when we do this measurement, we will know exactly where we are in this Hilbert space, and we can correct it back. And this root 2 just comes because the action had this root 2 for displacements in the phase space. So yeah, this is a simple GKP code. You can define it for any separation. You can define it for any Q. You can encode any amount of information in there, any amount of distance. And the distance is simply given by these values of the separation. Um, let's see the stabilizer structure of these codes. So these codes are stabilized by these operators, which are 2 pi I q over alpha and e to the minus I d p over alpha. So these admit your moment position states as eigenstates. Q is actually just equals to x. Maybe I should have mentioned this. And these are eigenoperators for the momentum states. But more interestingly, these are also the displacement operators in these particular bases. So this guy, if you act on a position basis with this guy, then you just get p plus I think just 2 pi over alpha. Yeah. So if you start out in any state p and you apply this e to the I 2 pi I q over alpha operator, then you are just moved to this other state. So these are displacements in the phase space, these two operators. And this acts in a similar way to this acts like this for the position states. X plus d alpha. Yeah. And these are the stabilizers because if you apply if you apply this operator on any of the states in your momentum space, then you're just shifted by some integers of these displacements, which takes you back to your original code state. So this guy shifts you here, 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 and so on. So these states are stabilized. And if you act with SZ on these states, then you are shifted again to here, here, and here. So these are the stabilizers of these codes, and it's not very hard to check that these also commute, which is an important property for stabilizers. And you can check this because of this Baker-Campbell-Hausdorff formula, um, plus some function of x comma y. So this operator e to the x comma y, why did I mention this actually? Oh, this was just to say that, okay, e to the x comma e to the y commute if and only if x comma y commute. And these things commute because of the relation we saw previously, because of these displacement operation relations. If you check this for the operators, then this happens to be the case, and this SZ and XX are actually commuting stabilizers. So this stabilizes your GKP codes, right? We can look at the Wigner functions of these things. Those are quite instructive also. So if you take this kind of GKP code and you plot the Wigner function in the phase space, then it's just an array of these peaked probabilities in constant intervals. So in constant intervals of here I've taken alpha equals to root pi to plot. So these are peak probabilities which are separated by alpha or which are separated by alpha and 2 pi over alpha in the momentum grid. So with alpha and 2 pi over alpha becomes the same thing if you choose alpha equals root pi. So these have separations of root pi, and these also have separations of uh, yeah, root pi. So these are just these grids on the phase space. One other thing to mention here would be to that these GKP codes, the ideal GKP codes, are they have infinite energy because they are these superpositions of states which have infinite momentum or all momentum from minus infinity to infinity formally. Then they are formally infinite energy states and they're not practical. So how one would implement GKP codes is we would put a sort of Gaussian envelope over these states. So for example, if we have these states and this was, let's say, x equals 0, then we would put this Gaussian envelope to reduce the contribution of the states which are further out from 0. So this can be implemented by this sort of operator. And if you put it on a GKP state, then the energy becomes non-infinite because the contribution of the higher energy states is exponentially suppressed because of this operator. So, and these are the sort of Wigner functions, what the Wigner functions look like when you apply this approximation or you apply this envelope to reduce the contributions is when you have a very low epsilon, this includes a lot of these high position and momentum states. But as you keep increasing your epsilons, then you see that the contributions start getting concentrated more and more towards the center until for very high epsilons you just have this vacuum state which is concentrated at x equals p equals 0. So this is just one coherent state, and this would, as you can imagine, like if you have just this vacuum state, then this is pretty useless for error correction, whereas this would have better error correction properties. So you trade off this practical feasibility or this energy of the state with the amount of error correction you can perform with these states or the performance of this error correction for the GKP codes. But in lab, you would definitely have to implement some sort of this attenuation so that the states actually become practical or feasible to implement. Um, yeah, so that was the construction. And finally, I can talk a little bit about the performance of the different kinds of codes we have seen till now. So this is from a very interesting paper back in 2018 by Victor Albert and some other people at Yale. They compared a bunch of single mode bosonic codes against the loss error channel. So this performance comparison is only against this loss error channel. Um, so what's plotted on the y-axis here is the proxy performance. So the higher the value, the better the code is performing, and this thing is the error rate. So if you go more towards the right on this x-axis, it means that your system is more erroneous. So they took a bunch of these codes, which are GKP codes, binomial codes, and CAT codes, and some other codes which were these numerically optimized codes, which we haven't talked about. But these were the major families, and they compared how these codes perform against the loss error channel by choosing the best members of each of these families, or the comparable members of each of these families, and taking their best performances. And the results were sort of surprising, which because of this. So if we look at this region of, let's say, gamma greater than 0.2, we see that GKP codes perform better than these binomial and CAT codes. And this is surprising because GKP was designed to correct against displacement noise, whereas these were designed to correct against loss errors. And we are actually comparing the performance of these codes against the loss error channel. So even though the GKP codes were not designed to protect against loss error channels, they turn out to have the best protection against this loss error channel. So that was a little bit surprising. Um, but another interesting point in this performance chart was that if you go to low enough gammas, which is this smaller plot here, it is the same plot but just zoomed in this region. So you have values of gamma very, very low. And in here we see that the CAT codes and the binomial codes actually perform better against the GKP codes. And this is also sort of intuitive to understand because since I mentioned these cats and binomials were designed for loss error channels, if you have a very low error rate, then the system would only experience a single photon loss, essentially. And since these codes can protect against the single photon loss exactly, whereas the GKP code is always going to be approximate for the loss error channel, then for very, very low values of gamma, where only single photon loss happens, um, then the cat and binomial codes perform better. But for all practical purposes, I think like your loss error rates might not be in this very low error regime. So then the GKP codes just perform better in every sense. They definitely perform better against the displacement noise, and they also protect better against these loss channels, even though the other codes were designed specifically for this channel. So I guess one interesting takeaway from this is that just looking at the exact error correction performance or these nil-of-alarm conditions doesn't give you the whole picture. So you can construct codes looking at these conditions, and they can serve as guidelines, but the actual practical performance might not be on par with just these formally rigorous codes which protect against these loss channels or the error channels on paper, or they protect against these error channels exactly. The approximate or the approximate error correction performance becomes quite important when we're actually working with these codes in the lab. So yeah, that was mostly about the constructions and what I wanted to say. I can just mention a few of the more interesting directions if people want to study further, which is one of them is this lattice GKP codes. And I kind of mentioned this earlier also that these GKP codes can be implemented in multiple modes and they can also be implemented in different configurations. So the examples we saw was just the square GKP code where there uh, where these like separations were sort of in the square lattice of phase states. This is also what we saw in the Wigner function, but you can actually define GKP codes on a multitude of lattices, which are which can give you different displacement properties and so on. So for one of these is, for example, the hexagonal lattices where these points are distributed on a hexagonal lattice. And this would give you better protection or different kind of protection against this displacement noise. So you can play around with those and create all sorts of exotic GKP codes. And this is all within a single mode. But then you can also have multimodal codes. For example, in GKP codes, you can have this degree of freedom with different lattices, but you can also include more modes so that you have these 3D or 4D or however many dimensions of lattices. And you can define your GKP family on any of these lattice. So all of these points would sort of be the states which are superposed to create these GKP code states. Then you can have multimodal codes in other families as well, like the cat family. You can have like multiple cats just working in different modes separately. You can concatenate these things. Recently, there has been work on more interesting families of multimodal cat codes, where the most prominent ones are these tiger codes and the quantum spherical codes. These tiger codes are actually these infinite superpositions of curves which are on the torus. So a zero code state would have contribution from all of the states on this black curve, and the one code state would have contribution from this white curve. So, and these have very interesting properties in terms of just like geometric properties, which yeah, they have interesting geometric properties, which essentially guarantees that you can protect against the loss error channel. And then the separation between these curves tells you how much the dephasing you can correct. And in a similar way, we have defined these quantum spherical codes, which are superpositions of points on the sphere. I've shown a torus here, but that's just a subset of the sphere. So you can have points on a sphere, and if they have nice geometric properties like spherical design properties and so on, then those are actually sufficient to get loss protection also. So there's all sorts of exotic ways to encode information when you have these coherent state family or these coherent states as your basis. And yeah, there's a lot of work to be done in both of these families and more, and in bosonic error correction in general, especially multimodal error correction. Some other sort of divergent interesting directions are how to do logical gates with these codes, how to actually do measurements in experiment, how to prepare these code states, or how you can efficiently concatenate these bosonic codes with qubit codes. This is sort of very interesting direction. Um, so maybe let me just give a little bit of an idea of this. So I think Kishore talked about the repetition code where you have 3 qubits, which are each two-level systems. So each of them are two-level systems. But what you can also do is you can have these 3 systems, but then all of them could be these simple harmonic oscillators. So you are sort of encode using the bosonic properties within each individual system, and you are creating another error correction code on top of it, which is this repetition code. So like this, let's say we had this binomial code in each system, and then overarching this, we have this repetition code through this concatenation. So you get sort of this double error correction from coming from this binomial as well as repetition code. And if you do larger versions of these, for example, encoding concatenating surface codes with binomial codes and so on, people have shown that you can get good thresholds for these codes, and those can actually give you better performance overall. And that's sort of one very interesting direction of research for these bosonic codes as well. Okay, so I let me stop there actually, and if we have time, maybe we can take some questions at this point.
Yeah, thanks, Shubham. I have a question, but maybe yeah, I think Lorcan maybe just unmute and ask here.
Yeah.
Yeah, thanks for the. Can you hear me?
Yes, I can hear you.
Yeah.
Yeah, it's very interesting. So I had one or two questions on the cat code.
Mm-hmm.
So you have this dephasing, and
Yeah.
I guess represented as like a coherent rotation. In practice,
Mm-hmm.
is it like a sort of integral over all, like a Gaussian distribution of coherent rotations? Like,
Yeah.
this is
So
like, okay, yeah.
yeah, so the error channel would again just be something like this additive white Gaussian white noise where you have lower contribution from these like higher
Ah,
order rotations.
okay,
And yeah,
okay.
but
So
just to
then,
simplify the analysis, I mentioned it in terms of this operator. I mean, even for the loss channel, the channel doesn't exactly look like this, but you can approximate
oh,
it
I
as just
see.
being powers of this loss operator
Yeah,
so that we can actually create codes.
I see. And so then, when you're correcting for the rotation, the dephasing, the phi,
Mhm.
obviously you need to learn phi to correct for it. So then, is there some sort of like a information theoretic limit, like from the Conor Fisher information, on how well you can do this, or something like that?
I wouldn't think there would be a limit because so when you want to learn phi, you're not. I mean, one thing is like you can try to just measure the state and you would learn the actual phi, but you don't want to do that because that would collapse your codes as well. So you try to measure these um, phi up to some modulo, like modulo, I don't know, some quantity a, where this a is determined by the actual code you're using. But
Yeah.
I'm not sure if that's what you were asking.
But then, even I just would have thought you can't do that perfectly.
Yeah, you probably can't do that exactly perfectly, but you can do that to a good approximation. Um, and actually, the point is not even that for these CAD codes usually, because if you see that I think the way the CAD codes were meant to be, or like the reason they were motivated, is because, for example, in this two-legged CAD code, all your code states are highly separated. So, like the simplest example of this CAD code is not even the thing that I showed. So the simplest example of a cat code is just this, where this is your zero state and this is the one state. Now we would say that the dephasing noise is actually exponentially suppressed because the only way this dephasing noise would affect the code is when your zero actually goes into this one state, but this is a huge jump. So this noise is actually exponentially suppressed, so you don't even need to really correct against it. You can have some sort of like you can have some sort of passive error correction in the sense that you put your system in an environment which has only these 2 points as your steady state, and then this can go on the side while you do your active error correction for the loss errors.
Okay, I
So you
see.
don't even need to actually measure this syndrome and then correct actively. You can just put it in an environment with these two steady states. And that's, I think,
Okay,
how typically these bosonic or these coherent state codes are implemented. Does that
that
make
makes sense.
sense?
Yeah, thank you.
Thanks. There was one other question from Narsimhash Varun.
Yeah, hi, thanks.
Hi.
So it's my question is related. So you kind of answered like satisfied my the practical aspect of it, which is what would you do, which is you said you don't even have to measure the syndrome, but if you
Yeah.
did, so I can imagine if you're just trying to determine the phase, you could do like a homodyne measurement with respect to a coherent state, and you learn sort of but you don't want to do that because you have a superposition of two
Yeah.
coherent states. So
So
what,
yeah.
like even formally, what would be a kind of measurement that, like, let alone practically, what would be a measurement that would tell you the phase without,
I
disturbing the
mean,
superposition?
exactly this thing, right? Like, for example, in this cat code, you would boomer moments. But for this cat code, like you would want to measure the phase modulo mod pi over 2. So if you measure it in this region, let's say.
Right, but what is so for example, a parity measurement, I can imagine it as a, I can write down a projector onto the all of the even Fox states or all of the odd Fox
Mm-hmm.
states. Like I can imagine a formal POVM for the
Right.
phase. What would that even be?
Interesting. Let's see. I guess if you want to write down a POVM, and I'm not Yeah, I'm not sure if it would exactly work this way, but in principle, you can just write down like a coherent state where you take, let's say, so this point and this point would correspond to the same value of phi mod pi. So you can just say like this psi 1. I'm not sure if this is exactly how it would work for coherent state, but it seems like this would be the projector for measuring, let's say, if this angle was theta, then this would be the POVM operator for theta, yeah, theta mod pi over 2.
I see.
But
Yeah,
I'm not
yeah,
sure
that
how
kind
you
of
would,
makes sense, I think. Yeah,
I'm not sure
thanks.
how you would implement this with your
No, yeah, I'm
actual
not even
practical
thinking
measurements.
about
Yeah.
the implementation, just sort of I'm trying to grasp the concept of measuring the angle,
Yeah,
the
yeah. So you
phase.
want like you want these antipodal points to be identified so that you don't distinguish between these points, and you would do this for each of these. Yeah,
Got
each
it.
point on the
Thanks.
circle.
Okay, thank you.
Thanks.
Yeah, I have also a question, but I mean, maybe
Yes.
also related to measurement only. So, like all the codes that you mentioned, Shubham, like they are basically example of subspace codes, and
Mm-hmm.
every time you have a, let's say, a vector subspace or vector space, it corresponds to. I mean, you can find a matrix whose kernel is that subspace. So
Mm-hmm.
and that matrix normally in regular quantum error correcting code is the parity check matrix.
Right.
So I was saying that you know I mean maybe it already exists, but do you know, I mean, like, what is the notion of LDPC that people think of, and is it somehow related to that matrix whose kernel like will correspond to
Mm.
like these codes are in?
So I will definitely not have a concrete answer for this, but I would imagine maybe LDPC would be something like um. So there's two notions of LDPC I could think of. One is just like having a low number of modes, but maybe that's not so interesting. The other notion I can think of is having a low support over this phase space or low support over your Fock state space. For example, these binomial codes, they only had like 4 states for the simplest code, for 5 states for this single correction code. So I can imagine having families of these codes where you have like so what I'm imagining is like the number of states that support the code space.
So it's
This could be sort of the proxy of your n for qubit codes, and then k and d works in a similar way. Like d could be just the loss distance. And so you can imagine, I mean, this is like I'm talking about the parameters because I'm thinking of like good families. But I think
like
maybe LDPC would make more sense thinking of this number of states where you can truncate your Hilbert space. But I don't know if that makes a lot of sense in the bosonic world, like LDPC codes. Um,
Yeah, like what are yeah, exactly my question? What are bosonic LDPC codes? And like I mean, on something related to that, I was thinking. I mean, so you have, I mean, okay, so like there are these bonds, right? Brabby-Pauling Tehral
yeah,
bond and other bonds, like uh, which tell you like what are the bonds when you on the parameters like that you were talking about
yeah,
M, K,
yeah,
and
yeah,
D, when you have locality constraint or when you trade off some locality,
yeah.
like yeah. So like those kind of like basically the bosonic analog of Brabby-Pauling Tehral bond or
Yeah, so I can
like
definitely answer you a little bit more on that front is I think those bounds are not very well studied as of yet. Even the analog of the Hamming bound and the Gilbert-Vershamov bound was just I think it was studied just last year from Ansgar in Berlin, and he had a paper out which talks about some of these bounds. He uses all of these McWilliams weight enumerators and so on to characterize the Hamming bound and this Gilbert or Shamov bound, and some other bounds which I don't completely fully understand as of yet because it's very mathematical. Um, but so I don't think there's any notion of like Bravi Terhal Bravi Pulin bound for like when you constrain to localized codes because I don't even think there's like a good notion of locality to begin with. So those bounds are very understudied for bosonic codes till now for sure.
I see, okay.
Yeah,
Okay. Thanks. Yeah,
but
seems like
then
quite a young field. I mean, compared to the
yeah.
regular qubit, the
Yeah,
discrete.
definitely. But this idea of like a parity check matrix analog, I think is interesting. That would also help like form like a general error correction theory of bosonic codes. I never thought
Exactly,
of it
because,
in
because
that way.
it has to be, like some matrix whose kernel, like that subspace will be.
So I
And
think the other
yeah,
thing would be like you can maybe have that matrix and like theoretically you can comment on the parameters of this code or the performance of these codes, but then that matrix may not be something physical that you can actually measure. For example, in the qubits, you have this matrix, you just measure some X operators as the operators on those particular qubits. But here,
yeah.
like the matrix would have like the ambient space of this matrix would, let's say, be this coherent space, like this C to the D, some complex space. Now, what do you do with this thing? It's maybe not a valid measurement.
Like if you have some, say, GKP code, which
Hmm.
essentially is like each mode can support one qubit, right?
Hmm.
Uh, and then if one cheap way of doing all this would be to just concatenate that with qubit-based codes, like you
Yeah,
mentioned, and then everything n would just be the number of modes, then, right? The number of physical modes you have, and then k would become the number of encoded qubits in that. You could presumably, at least for that family, those kinds of things where each mode more or less functions like a qubit, you could do that.
yeah, yeah. So yeah,
And then
I mean,
LDPC could be defined by like uh, on how many modes at a time do you have to make these check measurements.
yeah, that I agree with that, but that also seems like a very simplistic notion of LDPC because you're not really taking advantage of this. I mean, you're treating each mode as a single qubit, so that's the same notion of LDPC as in qubits, but you can, for example, encode a qubit rate or a qubit in a single mode. So I feel like those would be more sophisticated models, and maybe it makes more sense to and form a notion of LDPC while incorporating this degree of freedom as well. But I mean, yeah, maybe for a first pass, I think that could be interesting to see if you get anything different by just treating each mode as one qubit. Um, yeah, but but I would imagine like all the notions of normal LDPC codes would just carry over since you're still treating. Well, actually, no, because you have a one logical qubit in every mode, so maybe not. Yeah, yeah, interesting.
Okay, thanks, Shubham, then. And yeah, I mean, this was quite pedagogical. So I assume next week we will have Toby speaking on decoders. And
Hmm.
yeah, like thanks, Shubham, for this.
Yeah, thanks.
I think
This was fun.
quite good. Thanks a lot for.
Thanks.